Most of the drugs we give need to get into a cell in order to have a clinical effect. So how do they get across the cell membrane? What are the mechanisms by which this can happen? The simplest is passive diffusion, and this is very common, and it's simply diffusing down a concentration gradient. The drug goes directly across your phospholipid bilayer in your cell membrane, down its concentration gradient. No energy input is required, and the key here is a molecule has to be unionized. It can't be charged if it wants to cross this fatty layer. If it's charged, it can't get across. So an example here is lidocaine. So lidocaine has to diffuse across the membrane, and then it acts on the intracellular surface of the sodium channel. So it has to be unionized. It can't be in its charged state if it's going to try and cross this membrane, and that's why you don't give lidocaine into inflamed tissue, because the inflamed tissue is acidic. It turns the molecule into its charged version, and so it can't get into the cell, and therefore it doesn't do anything. The other alternative version of passive diffusion is if you happen to have an ion channel just sat there which allows, for example, sodium ions through. Those channels don't have any active energy input, they're just there, allow specific charged particles to pass through the membrane. The next option is facilitated diffusion. This is essentially diffusion down a concentration gradient, but it has a bit of help. So it will have some kind of membrane-bound protein, helps accelerate the passage of a molecule or a particle across the membrane. And an example here would be the glucose SLC2 solute carrier 2 protein. So the molecule is still going down its concentration gradient, but it's happening much more quickly. Next up, we have active transport, and this is for when we're pushing something against a concentration gradient. And we can have primary active transport or secondary. Primary is when we use energy to pump an ion against a concentration gradient, and the classic example is your sodium-potassium pump, your NAK ATPase, which breaks down ATP, releases the energy, and uses that energy to physically push sodium ions out and potassium ions in. They are going against a concentration gradient, so this needs active energy input. Secondary active transport is when you use a concentration gradient to push something against its concentration gradient. For example, the sodium hydrogen ion antiporter in the kidney uses a sodium gradient. So the sodium wants to come in because our ATPase has pushed loads of sodium out. That sodium wants to come in. So by using that gradient, we can drive hydrogen ions out. That is secondary active transport. And finally, we have endocytosis. This is for very large or very polar molecules that we can't use any of these mechanisms for. You bend your phospholipid membrane around the large molecule that you want to bring in, and then the membrane forms a bubble or vesicle by separating here, and you end up with a phospholipid bilayer vesicle with your drug inside. And that is endocytosis. These are the main ways that a drug or a molecule can get across a membrane passively or actively, depending on what the properties of the drug itself are and whether it's going against or with a concentration gradient. The vast majority of our drugs go through passive diffusion. We need a large concentration gradient, and we ideally want them to be in an uncharged state so that they can cross the membrane to get to where they need to be.